Hello YouTubers, and welcome to this, my second video about learning how to develop for the STM32 MCUs. In the last video we went through the different variants of STM32 and how to find the documentation, and we ultimately ended up installing the ST's development environment, which is called STM32CubeIDE, and we left it there. In this video, hopefully, we will be developing our first little application for the STM32 Hello World application, if you like. And as in the last video, this is unscripted, so I'll just play along and solve the various problems as I run into them along the way. Let's start by actually creating a GitHub repository. One of the most irritating things I know is people online making a post on Facebook or Twitter or what have you, saying my Blink application doesn't work, please help. Well, I mean, it's really hard to help if you don't know what is there. So the least you can do is actually give access to the source code before you're asking for help. So I will begin by creating a GitHub repository for these videos. So I'll go to GitHub. I'm already logged into my account here on GitHub, and I will create a new repository for where I'll put everything in these. We could call it STM32 Fun. Give it a description, STM32 Beginners Fun. We'll make it public, we'll add a README, and we will put a C, git ignore, and we'll just do the MIT license. I always pick the MIT license because I can't be bothered reading the others, and it is by far the shortest of the lot. So create the repository. We now have a repository we can use as a workspace. So I will copy the link to that and I will clone it locally. Now I usually put my stuff in source in my home directory, and we can now clone that repository that we just created. And here we go. So I have my STM32 Fun, and you'll see the files that were created over here are there. So now we can start our STM32 CubeIDE, which we installed in the last video. And we will browse to this new folder, STM32 Fun, and we will select that as our workspace. Launch. So here we go. STM32 CubeIDE running with that workspace that we just created. Now, before we even get started, there's a few settings in STM32 CubeIDE which I always change before I start. And so let's go into Window Preferences, and in here I will change the appearance of the fonts, the editor, and I usually change the font size. I'm getting old and blind, so I like to have it a little bit bigger on my monitor. The other thing I'm changing is under C++ code style formatter. The built-in Kernighan Ritchie C template use tabs, and it annoys me no end. So I usually create a new formatter, which I'll call C. And the main change I make is I indent by spaces, not by tabs. And I usually basically set very long lines because I don't want it to wrap. If I want something wrapped, I'll wrap it myself. So apply and close, and that's pretty much it. Now I have STM32CubeIDE configured the way I want it, and I can begin a new project. Before we begin the project, however, let's look at the documentation for what I intend to do it. In the last video, I said I would be using my own STM32 Weld modules, but I kind of changed my mind, and in this particular video, I will be using a black pill board with my own ST-Link programmer. So essentially, this will be the ST-Link programmer I use. And the interesting part about this particular programmer compared to the cheap Chinese clones is that I have a few extra pins on the header. So the target header, I'm using the clock and the DIO connected to the black pill board, but I also use the SVO and I use the serial line. So I can do serial debugging, I can do SVO debugging. I'll get back to how exactly that works later. So I will also be using my black pill board, a black pill board, it's not mine, for the development. And actually I have a photo up here which shows exactly what I have right now. So I have my ST-Link programmer and it's wired up to one of these standard cheap black pill boards. If you buy this off AliExpress, we checked in the last video, it's about $5. So that is what it will cost you to get going with something like this black pill. Now, before we start, let's make sure we have the documentation for everything that we want to do. First of all, let's look at the schematics. So if we look at the schematics for the black pill board, also I have a link down here called board info, which is interesting as well. So let's look at the board info first actually. This is the kind of module we have with the extra button. So it's a black pill version 2. Oh, okay, they're both the same, I think. So interesting here is this. The external crystal, which is a 25 megahertz crystal, that is important to know for later. Another thing that is interesting here is the user button. The button is connected to PA0 and it's active low, meaning when you press the button, the signal go low. Otherwise, it will be high. And I think there's one more thing we need to know. The LED. How is the LED connected? User LED is connected to PC13, right? And it's in sync mode. Sync mode basically means it's connected to 5 volt, and you have to pull the pin PC13 low to actually switch the LED on. We can also look at how that looks in the schematics. Up here we have the key. It is just connected to PA0, and when you press the key it goes to ground. This means that we need to pull it up somehow. We'll get back to that when we actually write the code for this device. And over here we have the LED, and you can see it's connected to 3.3 volt and goes straight into PC13 through a resistor. So if PC13 is high, the LED will be off. If PC13 goes low, the LED will light up, hopefully. The last thing we might need, but let's make sure we have it, is the datasheet for the processor in question. I don't think we'll need that for the first video, but just to make sure we know where to find it if we need it. it's an F11. We can see that in the board info. Where is it? Here. It's an STM32F411CEU6. And if we look over here, we have the data sheet for that particular processor, STM32F411 something C. Oh, E. Sorry, it's the E version that we're using. So it's this one. So it's STM32F411CE. C essentially indicates how many pins we have. We can see this in the data sheet if we scroll down after the table of contents. We have an overview, so we have the E version here with where is it? I think it's this one. It's the 36 pin. It's U. It's probably one of these two, UF, whatever. It's one of those. It doesn't really matter at this point in time. So now we have all the information we need. So let's start a new project. So we go over to our STM32CubeIDE and we simply create a new STM32 project. When that happens the first time, it will be a little slow because it might, don't know, it didn't. It actually came up pretty fast. So we can give it a part number, but we have to select which part are we developing for right now. So we take STM32F411CE. That was the one, and U6. So this is the MCU that we are going to use in this project. You see here it is an UFQFPN unleaded quad flat pack, something like that, with 48 pins. And we select next, and we have to give the project a name. Let's call this Black Pill Blink. And we finish. So what will happen now is that STM32, based on the MCU we selected, will generate the source code for our particular project, a basic template source code. Of course, it will have no functionality. It will also launch what is actually an application made by ST called STM32CubeMX. Now that is available as a standalone application as well, but it is also built into the STM32CubeIDE, and it is a major time saver, which I'll show you once this first time. It takes a little while to get this fired up. We'll just patiently be waiting for that. Okay, we are back. Now I know what is happening here. First time when you just install STM32CubeIDE, it downloads all the support libraries and stuff like that, and you can actually see down here, that it is still downloading some software updates and various libraries and stuff like that. It will happen every time you select a new processor in a given STM32 CubeIDE installation. Anyway, as I mentioned before, it has now started what is known as STM32 CubeMX, but it is actually a built-in application in STM32 CubeIDE. It allows us to configure the various pins of the device as well as internal peripherals and stuff like that. And it is, especially for a beginner, a really helpful tool because these MCUs are quite complex. So over here we have an actual representation of the MCU with the various pins, and as you can see right now, none of the pins are actually used for anything. So let's start configuring this MCU, how we intend to use it. We start under the system core, under sys, and we need to enable the debug interface. As I mentioned in the first video, we are going to use serial wire communication with the ST-Link device, and you see we have the DIO and the clock signals out on two of the ports, which on the black pill board are connected to the header. We can have a look at that. Where is it here? If we look at the black pill pinout, you will see that the programming header is actually PA13 and PA14, which is lucky because those are exactly the pins that are connected to the serial debugging. Now I'm actually going to enable trace asynchronous serial wire. I believe it's SV is for serial wire viewer or serial trace, which goes out on another PB tree. Now you will notice that on the board PB3 is not out on this programming header, but it is on one of the headers up here. Where is it? PB3, it's there. Right, so that is actually the SVO signal. It is also listed over here as SVO. And I have connected that to the ST-Link. I have also connected, no, I'll get back to that later. So this is the basic pins we are going to use. We are also going to use the LED, and that was, if you remember, connected to PC13. So we are going to make PC13 a GPIO output. I will also rename it and call it LED to make it easy. I also had a button on this board, and that went into PA0. So we could set this as a GPIO input, but I'd rather make it an interrupt so we can actually respond immediately to a press of this button. So we make this an interrupt pin and we call it button. So this is basically the basic pins I'm going to use. Let's go up to the GPIO and configure those a little further. So we have the PA13. Now, if you remember, it actually, when it was high, the LED would be off, and if it goes low, the LED will be on. So I'm going to reverse this and set it to default to be high. That means the LED does not light up, and rather than using push-pull, I'll just make it open drain. So it cannot pull it high, but when it goes low, it'll just drain the current supplied through the LED. We also have our PA0 here, and if you remember, that just have a button that goes to ground. We want to respond with an interrupt when it goes high, rising and falling, but we will also pull it up because the button is basically pulling it down to ground. So it will default be high. When you press the button, it'll go low. The final thing I'll do here is under connectivity, I will enable the UART for asynchronous serial communication, and you can see over here that actually goes to PA9 and PA10, transmit on PA9. So PA9 will have to be connected to the RX pin on our ST-Link device and vice versa. I have not bothered connecting this one because I don't really plan to use the serial communication. I will also set it to run a little faster. In my experience, 921600 is a good speed to run it. It works very well. I'll go up. Final thing we want to do is configure our clock. Now, up here under the system codes RCC, You see, right now we are using internal clock only, but we can configure the high-speed clock to actually use the crystal on the board. And we will do that. You'll see that that actually set the oscillator to run on pH0 and pH1. And again, let's look at the schematics for this board, which we have here, the MCU, and you will see pH0 pin 3 and pin 6 are running to the crystal. Let's look over here. That is pin 5. Oh, pin 5 and 6. What did I? P8. Oh, it is 5 and 6. I'm just getting blind, as I mentioned earlier. Final thing we need to do is on the other tab up here, clock configuration, we can see the internal clock circuit in the MCU. And you can see at the moment it's actually using the internal RC oscillator running at 16 megahertz, and that is generating a 16 megahertz clock internally. But we want to switch to the external crystal, so we click down here. Now we're using a 25 megahertz crystal, and we want a result running this full speed, so that is 100 megahertz. If we click there, it will actually use the 25, no, there, didn't do it right. So here, so the 25 megahertz input frequency will be divided by 12, multiplied by 96, and divided by 2, resulting in 100 megahertz internal clock. At this point, I should mention that the timer clocks over here are also running at 100 megahertz. So that's pretty much it. So that is our basic configuration, and we can now generate our code. We click generate code. And STM32 CubeMX or STM32 CubeIDE, depending on how you look at it, will generate a basic source code for this device. Now the organization is a little weird, but we have the core, and in core we have a core include and a core source, and that is our main C. The way CubeMX or CubeIDE is doing is that all these source codes are templates. So you will see throughout the code you have these user code begin and user code end, and whatever you change in between here will never be modified by CubeMX. Let me give you an example. Say we want to include a header and we put it here. We can include stdio.h. We save that. If we later go back to CubeMX and generate the code again, you will see that this line actually disappears because CubeMX owns all lines outside these user codes. So if we want to include stdio, we have to put them in one of those blocks. Fortunately, they have a private include block here, and we are going to put it here, stdio, and you'll see now if we go back and we generate the code again, that line will not be modified. It will still be there. So let's look at this main C and get an overview on how this is actually put together. You can see in the beginning you have the user code include. You have some type defs. You can put your own type defs here. If STM32 CubeIDE MX wants to include one, they will put it up here. There's some defines, and you can see down here there's some variables. In this case we have one handle for the UART that has been defined up here we have a section here where we can define our own variables. We have a section here which we will use to fill in our own code outside the main loop, and then we have our main function down here. The main function will start by initialize hell. Hell is the hardware abstraction layer that is ST's standard libraries. It will initialize the system clock, it will initialize the GPIOs, and it will initialize the UART. These will change depending on the settings we have over here. Just to show you an example, if we went down and say we want to include a SPI and we have a full duplex master SPI, if we generate the code for that, you will see that an extra initializing of that will be added. Let's disable that again. We don't need that at the moment. Project generate code. So here we go. You'll see after the main function, you will have these functions for the system clock config. You can see here exactly what it is doing, how it's initializing. It sets the high speed external, and you will have the clock dividers. And I mean, you could in principle modify this so anything you want. No guarantee it'll work, but you could set it to anything you want. But be aware that if you do it outside these user blocks, it will be overwritten by CubeMX if you ever regenerate it. So again, if we want to do some extra in the UART initialization, we should put it down here, or we should put it up in these user code blocks that are prepared for us in this. So this is it. This is a basic application that does exactly nothing except initialize. Let's try to build the project so we can click build project, and you can see down here, we can make that, maximize that. It will compile all the source code files, and it will end up with an ELF file which we can use to flash to our device. We can also see over here that it is currently using 7.36 kilobyte of flash memory out of 512, and we have static variables of 1.6 kilobyte. So that is the basic application. Now let's actually do something. And one of the things we had was we had our UART, so we can do serial communication. So if we look over on my website, I have a page with describing serial debugging, and an interesting part here is a function down here that I'm going to copy. And you will see this is user code 0. So it goes into this block. So we basically paste that in here, and you'll see what it's doing. It's actually overriding the built-in write function and redirects that write to the serial port, so it will transmit on UART 1 whatever is being printed out. We can now try down here in the main loop. After we initialize the UART, let's print something. So we can do printf first application starting. Let's try to build this. Before we used 7.36, you will notice that now it grows a little bit because it probably includes. Actually, it didn't. So it's about the same. So before we flash, let's fire up a serial monitor. I usually use microcom, and notice I set the speed to the 921600, and I fire this up, and let's flash this application. Up here we have a run button. So if we flash this, first application starting, oh, sorry, it comes up the first time you have to select the debugger, but all the defaults for now are fine. So it is now complaining. I think in the last video I updated the ST-Link firmware, but that was another ST-Link than the one I'm using now. So let's update. So we open this in update mode and we flash a new firmware on the ST-Link device. Takes a few seconds, reasonably quick. And that is it. We will notice down here, because it restarted, I lost my serial signal, so I'm going to fire this one up again, and I'm going to run the application one more time. And let's look at the output. Look, first application starting. Flash again. First application starting. You will notice there was some other output up here. That was whatever application was in my black pill before I started this. So, but it's essentially running the application and it's producing some output. Let's do some stuff down in the while loop. Let's print a statement occasionally. So we do this the wrong way. We can basically do a printf loop, just type loop, and then we set a hell delay. Oh, we do a hell delay of 1000 milliseconds. That should print loop every 1 second. Flashed. There you go. One thing I absolutely despise is the use of delay anywhere in an embedded application, because you might want to do something else while that you're waiting. So I will usually keep a track of the internal clock. So I will do a variable called now, which I'll set to 0, and last print, which is 0. And down here I will say now there is a function called getTick, which will return the number of milliseconds since the MCU was booting. Then rather than doing the delay, we can simply check if now minus our last print is greater or equal to 1000. Then we'll print our loop and set last print equals now. We can remove this. This should, we can also say loop and we can add now, just now. Save that, build and run. And there we go. So it will still run every second, and it will print out the now variable, which contains our number of milliseconds since we began this thing. Now, I think this video has become long enough, so I will skip the debugging to the next one. Before I finish though, I will go in to my STM32 font folder, my workspace, and you will see I have the black pill blink folder here. I will add that to Git, I'll commit it. First project. And I will push it to GitHub. Now let's look at, do I have my GitHub here anymore? No, I didn't. So let me open and look at my repositories, and you will see that I have an update just now where my Blink is. Now, of course, the purpose of this is, first of all, me keeping track of all my stuff so I'll never forget, but it also gives me the option, if I have a problem, I can simply send a public link to this and people can go in and see exactly what I was doing. Okay, that will it. In the next video, we will start to play around more with the debugger in STM32 CubeIDE. I actually originally planned to include this in this video, but it's already getting too long, so I will stop now. See you next time.